Good morning, America. Good evening, Asia. Many of you know me from my background in carbon nanomaterials, fullerenes, nanotubes, but you do not know me about working in water. I realize that it is maybe these materials that hold the key to the answer how to provide potable water to everyone in a cheap, relatively cheap way, because water and access to potable water is number one problem of humankind. Let me first introduce the topic. Now, we have a lot of water around us. So what is the problem? The problem is that salty water in the ocean or dirty water can cause harm to humans. Separating water from salt in ocean water is not easy. So I want to propose specific carbon nanostructures to help in this problem and to provide a paradigm shift for the system. This is a film of these nanostructures, and I will talk to them later on. As you see, hopefully only water can get through, whereas chlorine, sodium, other ions would be rejected. My collaborators, I'm not sure why they are red arrows on the screen, but Andrei Kirillchuk is a Ukrainian scientist who visited me for a year. He did most of the work. Pranav Surabi was a Indian graduate student who spent a summer in my lab, in my virtual lab, did most of the calculations for a second part. And Barbot Naderi is an absolutely wonderful high school student from Tehran, who was very interested in getting the atomic scale processes. And yes, we had some financial support. So let me introduce the outline of my talk. First, after dealing with water shortage, I will talk about a search for better membranes for reverse osmosis, which I will introduce, then our computational approach, then I want to validate our computational approach, and then I want to get to results. Flow across a graphite oxide membrane and thermal cleaning and thermal stability of those membranes, which should surpass the current technology. At the end, I will summarize. Once again, water shortage is the toughest problem of humankind. So where is all our water? Look, most of the water, 98%, is in ocean seawater that contains salt. Only 2% are not salty water. We would call them fresh water, but sorry, they also contain brackish water. And if we look at this small fraction, 80% of it is in permanent snow and ice. So we only have access to 20% of this 2.5% of the water overall. This is very little. Now, we would like to access seawater, but it is salty. So we have to desalinate, and this is an extremely tricky problem. There are several technologies to do this, and one of the leading technologies is reverse osmosis, RO. Let me show you how it works. Let's have a container filled with water. As a matter of fact, it's a U tube. And the salt ions are on the left-hand side. If they would be free, they would spread overall in the tube. However, I put a semi-permeable membrane so that only water can go back and forth, but the ions are rejected. Next, I will apply a pressure. Look, without that pressure, the fresh water will go in the direction to the left so that the ions would be there would be very low concentration of ions, as low as possible. In order to counteract this action, the osmotic pressure, we apply pressure, and as a result, we achieve water flow from left to right. We will have access to pure water. Now, the key component of the system is a semi-permeable membrane. It lets water through and it rejects ions. Let's see what we know about such membranes. There are problems with the current technology, which is polyamide typically. This is an organic compound that has limited selectivity of water with respect to sodium or chlorine, that is prone to biofouling. And if you were at the ocean at a ship, you see that there is biofouling at whatever structure there is. It has limited chemical stability. That means it cannot be cleaned by chlorine, and it has no electrical conductivity. It has also limited thermal stability, like most organic compounds, limited permeability, and again, organic spongy thing, limited strength. The membrane community so far has largely ignored carbon because they were not informed about advances in nanocarbons. Carbon for them had a bad reputation. Graphite carbon is essentially a brittle powder, so what would they do with a brittle powder? But the community is unaware mostly of advances in nanocarbon synthesis, meaning nanotubes, carbon fibers that are strong and that can be woven. Graphite and graphene are hydrophobic. However, graphite oxide, GO, is hydrophilic and its layers can be aligned. I will be talking in most of my talk about graphite oxide, what is known about it experimentally, and what our calculations revealed on top of that. The nanocarbon community, that's me, that's my colleagues in nanotubes, fullerenes. We have been ignoring water treatment. We focus on electronics and God knows what. I believe water treatment has a unique application. This could be even the killer application of nanocarbons, and I will introduce you more. Let's go back to graphite oxide. Graphite oxide has been synthesized by Brodie in 1859. And 100 years later, by Hammers, a new synthesis technique has been developed in 1958. In 1961, 3 years later, there is a curious journal article in Journal de Chimie by 3 German authors, Böhm, Klaus, and Hoffmann. It talks about graphite oxide and its membrane properties. If you look at the text in Journal de Chimie, everybody has to speak French. So, les membres d'oxyde graphitique sont imperméables excepté pour le liquide polaire comme l'eau. That means GO is impermeable except by polar liquids like water. Now, this is promising. Can we get microscopic insight? Well, there are lots of challenges. GO looks like a powder and is hard to contain. Even highly aligned GO flakes are still disordered. The presence of water in GO is essential. Without water, it's a different material. Water filtration is closely linked to the elusive structure of defects that change all the time. There are many reasons why a membrane does and a different membrane does not work. They are just obscure. We don't know why. Could experiment help us? Well, spectroscopic studies tell us about the chemical composition and bonding, and this is not much help. Electron-microscopy studies give us limited structure information about graphite oxide, but in absence of water. There is no simple way to study an operating graphite oxide membrane on the atomic scale. Theory, I will show you, is even worse. Realistic systems are too large for atomistic simulations. 1,000 atoms, and we will be using about this number, look ridiculously low to deal with the problems we are dealing with. Now, there are simulations that are not ab initio that are used on empirical force fields. Those empirical force fields have been tuned for either only bulk water, or only the interaction of water with graphene, or only graphene, or only carbon graphene oxygen, or graphene OH hydroxy group interaction. There is no valid empirical force field that's accepted generally for everybody. So look, if we are so limited by experiment and by theory, let us think first before we start calculating or observing. Besides graphite oxide, we also have nanotubes and carbon fibers at our disposal. And we could make a membrane out of those. Now, let's imagine a structure, a sandwich structure of all of those that could be a solution. And I will tell you about the component of the sandwich structure, but I can tell you, because it's all carbon, biofouling can be solved. You can clean it. Chemical stability, graphite, graphitic carbon, very chemically stable. Thermal stability surpasses all other elements. Mechanical strength, this is 100 times stronger than steel. Permeability will depend on the structure, and selectivity will depend on the structure. Moreover, if graphene will remain, or graphitic carbon, stable up to 4,000 degrees, well, we could use resistive Joule heating by passing current and by essentially burning any impurities and graphitizing. So this may be a possibility. Let's go to how to make it. The active desalination layer of graphite oxide are flakes that are maybe that are 1 micron across. Those flakes have pores. They have in-layer pores, let's say 0.5 to 1 nanometer. Of course, there will be bigger pores, and of course, there will be smaller pores. And you can imagine, if the pore is too little for water molecule to go through, it will be inactive. If the defect is too wide, everything will go through it, and it will be not selective. But a molecule has to go through a sequence of filters, and in that sequence, hopefully, we will get the rejection of ions and passage of water. Now, we will, because this is still a powder, we can sandwich it between 2 layers of bucky paper. Bucky paper is a substance you can buy on the market. It's essentially nanotubes that have been floated, because they are hydrophobic, on the surface of water. And on the surface of water, they float like a fleece. Like fleece of your jacket. You can harvest them, you can cut them with scissors, and you can use them for encapsulating the graphite oxide. Finally, to make it really strong, you can buy an all-carbon fabric. There are commercial manufacturers of strong carbon fabrics. This will be very porous. The pores will be very wide, so everything will go through. In the bucky paper, the pores will be large enough for water and for sodium and chlorine to go through, but stones will not get into the membrane. So we could get passage of water. Computational approach. Look, we use ab initio density functional theory like all ab initio people, because it has no prejudice. It's a bias-free calculation. It's not cheap, but it's bias-free. We use the Siesta and VASP codes. Again, no parameters, different exchange correlation functionals. These are not the only ones we use. We have polarization functions, pseudopotentials, molecular dynamics in the electronic ground state. Applied pressure on particular atoms could be modeled by forces which we apply to particular atoms. This is computationally very demanding. I guess I will get a question: can't you make it more predictive by making a more more quantitative exchange correlation functional? And I will say no, because even with this, we have very serious problems because of the time of the processes which we deal with. The timeline is about 1 second. In ab initio calculations in molecular dynamics, we typically can treat up to 1 picosecond, 10 to the 12 times shorter than we need. So please don't ask me for more quantitative and more precise functionals. We have also to carefully choose a relatively small representative system. Before I do this, I want to validate that's what most people in the field do not do. I want to convince you that this approach really works. First, in liquid water, which is known to be computationally very challenging, the hydration energy, that means the energy you gain when you put one isolated water molecule and let other water molecules surround it, the energy is 0.4 eV, and it is reproduced very well by our DFT calculation. The calculated gravimetric density is 10% lower than what we observe. Look, this is what we have to deal with. This is still better than what all other calculations have been obtaining, but it's still reasonable. The self-diffusion coefficient of a water molecule in water, which will be very important, it's 10 to the minus 5 centimeters squared per second, which is the same, look, up to a factor of 2, but same order of magnitude as in the experiment. Now, graphite oxide monolayer. There is a Lerv-Klinovsky model which has been accepted for 100 years to describe it correctly. We have graphene monolayer. Atoms above are solid circles, atoms below are open circles. We have atoms that are on top of a carbon. This will be typically an OH group, and there will be atoms that are in the middle of a bond. This will be epoxy bonds. The top view of the structure looks like this. The side view of the structure looks like this. Yes, it is a fat layer. Now, graphene graphite. We know that DFT is very precise in describing carbon fibers, nanotubes, graphite, graphene with 0.2% precision. But what about the interaction with water? The absorption energy of a water molecule on monolayer graphene is positive. So water likes to adsorb as a single molecule. But this adsorption energy is comparable to the experimental value. Now, we have to compare to the condensation and adsorption energy, which is having a monolayer of water. A monolayer will, of course, because the water molecules are interacting, will have a stronger interaction energy. Now, both values lie below the hydration energy of water, which is 0.4 electron volts. What does it mean? I am a water molecule and I have two choices. Either I go adsorb on a graphene monolayer and I gain 0.1 eV, or I remain in water and I gain 0.4 eV. Well, it is much more advantageous for me to remain in water. I will not touch graphene. Graphene will be hydrophobic. The same, now let's do it with graphite oxide. Hydrated graphite oxide is active core of our desalination membrane. Please don't forget. So adsorption energy of water on graphite oxide is much bigger, 0.7 eV, and this value is higher than the hydration energy of water. So if I'm a water molecule, I will much more prefer to be attached to graphite oxide than to remain in water. This means that GO is hydrophilic. This is what we know to be true. theoretical self-diffusion coefficient of water within GO is, look, very low, 2 orders of magnitude lower than in water. So yes, we expect all that. Our model system will be supercells. These are galleries of graphite oxide, graphite oxide, graphite oxide, separated by galleries of water molecules that can go back and forth. The dry Lerf-Klinovsky model in GO, the distance, interlayer distance is 6 angstroms, and it swells in presence of water to almost 13 angstroms due to water permeation. We obtain those results and reproduce them in our calculations. So let's talk about transport of ions solved in water across a membrane. Let me go back to the graphite oxide, to the paper by Böhm, Klaus, and Hoffmann. Les membres oxydatiques sont imperméables aux anions, mais perméables aux cations. That means they are impermeable to anions like chlorine, but cations can pass much easier. Why? Can our calculations explain it? Look, it is not a single cation that goes through, but it's a cation with its hydration shell that goes and travels through water. The hydration shells of sodium and potassium ions contain about 6 water molecules, and they are strong. If I should detach all the water molecules from the central cation, I would need 4 electron volts for sodium and 3.5 for the larger potassium. The hydration shell size is about 6 angstroms for sodium and a little bit smaller for potassium. So 0.6 nanometers, 0.5 nanometers for potassium. Let's keep this in mind. Hydrated sodium and potassium still can pass in between layers of swollen GO, where the interlayer distance is 13 angstroms. That's good. Now, what about chlorine? Chlorine is fat. Chlorine contains more 7 water molecules in its hydration shell, and the hydration shell is wider, so they cannot pass in between, or they have a hard time to pass in between swollen GO layers, and the pores must be much wider in order for chlorine to pass. So selectivity, primary worry are cations. The anions, they are out, they are too fat. So we will try to study either water or cations, or selective water and no cations. Let me first start with flow across of graphite oxide membrane. Water flow, of course, will be slowed down by the presence of graphite oxide because it has to go across the galleries. The water molecules in contact with graphite oxide are essentially stopped, and this is what the Hagen-Poiseuille law tells us. If water goes through a water hose, at the water hose water interface, the molecules are stopped. So, what is the effect of water pressure? Only the oxygen and hydrogen atoms are pushed horizontally in a force which is proportional to their mass. This is now artificial, how we make the force and how we put the pressure on water in the water hose. And this is what you see here, FO. This is our standard force multiplied by mass. And you will see that under this force, the front of the water column starts moving to the right. And they are accelerating. The water molecules at the interface are staying behind. But yes, water under this force can go across a defect-free gallery in graphite oxide. Now, let's talk about pores. If there are no pores in graphite oxide, there will be no flow across. Now, we have to be very specific. Those pores are essentially ripped apart pieces of graphite. This inlay of pores can have armchair or zigzag edges. They are not bare. They are chemically terminated by hydrogen or oxygen or hydroxy groups OH. pore width is measured in between the edge carbon atoms. So we have the armchair edge, you know it from nanotubes, you know it from graphene, armchair edge, zigzag edge. If we terminate it with hydrogen, this is what it will look like. Well, width, again, in between carbon atoms. We can, of course, terminate it with something else, with oxygen or with OH. And we wonder which of these is most important. Hey, if we have GO or graphene here, they are far away from the edge, so we can use the simpler graphene calculations. Now, once again, which is the most important factor for selectively rejecting sodium? Is it the type of the edge? Is it the termination of the edge? Or is it the pore width? I will convince you that unfortunately all those will play a role. I have a narrow 0.5 nanometer 5 angstrom pore, hydrogen terminated, and a wider 0.7 nanometer pore with the same edges. I put sodium plus in both, and I will let the simulation run. You see that we are putting pressure on water molecules, not on the other atoms of carbon and oxygen and hydrogen here. You see that over here on the right-hand side, the wider pore, though the sodium atom has passed, in the narrower pore, it has not. So in the narrow pore, look, in the narrow pore, you could say it might barely pass, but sodium, so water passes, but sodium is blocked. Let me show you. I have the water molecule above the pore at the height h. And I'm coming with the water molecule down, down, down. At each position of the oxygen atom, the entire structure is relaxed. I get the total energy. I move the oxygen down, relax the structure, move the oxygen down, relax the structure. I do it for different width of the pore. I do it for different termination, hydrogen, oxygen, OH, and I do it for different types of edges. You see that only for the hydrogen termination of armchair edge, the water would go through with no activation barrier, but for the other edges, there is an activation barrier. If I have sodium. Now let me do the same thing for sodium atom, sodium ion. I place it, I relax all the structure of graphite oxide. It goes down, I relax, it goes down. Look, you see that it depends on the type of the edge. Yes, the green, which is oxygen terminated armchair edge, the sodium will pass without a barrier. But not all our edges in a messy material are oxygen terminated armchair. But here, sodium plus would be attracted to the negative oxygen atoms and will go through. What about if it's hydrogen terminated armchair? It will have an activation barrier of 1 eV. Look, this is significant. There is an activation barrier for a hydrogen terminated zigzag. Again, a barrier, and the barrier is smaller for oxygen terminated zigzag. For a wider pore, I go from 0.7 to 0.9. Water, essentially no barrier independent of the edge and termination. Sodium at 0.9. Look, in most cases, for most edges, for the same pore width, it will be rejected. So here in this range, and we are playing 0.7, 0.9 nanometer pore width, we are playing, this is a pretty narrow range, but we have achieved selective rejection. Not only the width, but also the edge type and termination are important. One more thing. I have a pore of graphite oxide, and this water molecule would like to go through, but it cannot. The pore is very narrow. Let me compare this to the situation in a Western club. entrance to the bar. You have a swing door, and this cowboy, in order to enter the bar, has to kick in the door. So how can individual molecules, individual cowboys go? Well, there will be a concerted motion. If the cowboy enters, the next cowboy and cowgirl will be to enter much more easily, the third one as well. The same thing, if the first molecule opens the door at the edge, the next water molecules can do the same. Look, for 0.5 nanometer pores, we are always talking sub-nanometer. Water molecules with hydrogen termination, this is for an individual molecule. You have an activation barrier of 1 eV. For an oxygen terminated edge, for the same water molecule, the barrier is above 2 eV. It's too high. Now, in the concerted motion, one by one, it will be reduced. And let me show you how. Concerted motion, you open the gate. One molecules open the gate, the others can pass more easily. And this is, I believe, an important process that will allow penetration through very narrow pores. Now, I would like to talk about thermal cleaning of a GO membrane. Reverse osmosis membranes suffer from biofouling and must be cleaned. Polyamide membranes cannot be cleaned by Clorox, by chlorine bleach, because they would decompose. Graphitic carbon does not have the same problem, but graphitic carbon offers one more advantage. It could be heated up, and this technology has not been applied yet. Imagine the old Edison light bulb, incandescent light bulb that has a carbon fiber. If you evacuate the bulb and you light the fiber, why is the light emitted? Because the fiber heats up to a very high temperature. However, it does not burn. We could do it in an inert gas like argon, or we can do it in vacuum. The same way of cleaning might be applied to a graphite oxide membrane that has been used for some time. What will it do if this is successful? Well, first, the junk, the organic junk that is very stinking, will get off. Now, it will probably transform into graphitic carbon. Everything essentially goes ashes to ashes. So it will be graphitic carbon that might reinforce further the structure of my membrane. So organic residue would graphitize. Could such a geomembrane, we know about graphite, we know about carbon fibers, but what about our geomembrane? Let's heat it up. And now I have to tell you one important trick we are using. We want to know what happens on the time scale of 1 second. We cannot calculate 1 second. We have time steps in the molecular dynamics simulation that are fractions of a picosecond, and we can calculate up to 1 picosecond 10 to the 12 times shorter. So how could we get an information about 1 second if we only can do it in 1 picosecond? Well, the trick is you heat it up artificially. The chemist will tell you if you heat by 10 degrees Kelvin, the process will be twice faster. If you heat by another 10 degrees Kelvin, now the process will be 4 times faster. If you heat by another 10 Kelvin, the process will be 8 times faster. Look, by how much do I have to heat it up so that it will be 10 to the 12 times faster by typically about 2000 degrees Kelvin. So this is the trick we are playing here. We are artificially increasing the mobility and the time scale by heating up the system. I can get back to that. But look, at 1000 Kelvin, nothing happens. Yes, the graphite oxide is wiggly, but that's not much. At 2000 Kelvin, it's more wiggly, but water molecules are here and they are moving and they are happy. At 3000 degrees Kelvin, yes, it's wiggling a little bit more and the molecules are moving and they are still happy. I'm not claiming that it natured 3000 Kelvin. No, it will much, much lower. But I want to show you that there is a temperature where something happens. It happens to be 4000 Kelvin, at which temperature the carbon-carbon bonds break, the whole structure of graphite oxide melts. So in the calculation, it would happen in 10 to the minus 12 seconds at 4000 Kelvin. It may happen at a couple of hundred Kelvin if we let it stay for a couple of seconds. Now they must be performed. So how do we do our calculation? We use a microcanonical NVE, molecular dynamics calculations, because canonical constant temperature calculations require a thermostat, and the thermostat can horribly modify the dynamics. And so our temperature can fluctuate. So very short simulations, we have to increase the temperature. If graphitic backbone remains intact up to 2500 in MD, they will survive probably up to 1500. Maybe they will survive even higher. So 1500, 2500, look, there the first carbon-carbon bond breaks. At 3500, we have a destruction of the structure. We have also other conclusions. Water molecules do remain stable up to 4000 Kelvin and act as hot water vapor that will separate graphitic layers in an explosive way. The oxygen and OH group that are covalently bonded to graphene do not detach easily. The destruction of GO will eventually be promoted by the presence of existing defects or cracks. Once we have taken off that junk at high temperatures, we may cool down and we should get a defective GO structure that is similar to the system prior to heating, and that may be even better for the desalination of water. So cleaning by resistive Joule heating to moderately high temperatures may preserve those GO structures. So, in other words, constructing an all-carbon desalination membrane appears feasible. The water flows easily in between layers of hydrophilic graphite oxide. The optimum in-layer pores in graphite are between 0.7 and 0.9 nanometers wide. Water permeation requires pores wider than 0.7 nanometer. Selective rejection of hydrated sodium and chlorine is bigger, requires pores that are smaller than 0.9. So look, this is a very narrow range of pores. Imagine, however, that you have millions of layers of defective graphite oxide. One of them has wide pores, one of them has narrow pores, and a molecule of water, sodium, hydrated sodium ion and chlorine ion, have to go in sequence through all those pores. We believe that, and this is the original observation of Hoffman, that indeed, if the layer is thick enough, and thick may be 1 millimeter, if it's thick enough, you might obtain a selective rejection. So permeation is facilitated, we learned, by concerted motion across the in layer pores, one molecule opens the door and the others follow more easily. Finally, graphite oxide membranes may be cleaned thermally by graphitizing biofouling debris at 2000 Kelvin. So I am a little bit frustrated because we have tried in 1, 2, 3 publications convince the membrane community to construct a prototype membrane. We do believe that there has been a precedent, experimental precedent for desalination, but unfortunately the government programs are very restrictive. If you applied for a grant for this, you cannot do that. So I've been unsuccessful, but I hope that the wide audience, especially in Asia, where the restrictions are not so strict and where the benefit is much wider, will take the chance to assemble a prototype membrane. If anybody would need advice how to do it and where to get the components, I am very happy to provide help. Yes, I wrote a book that might be helpful in case you are new to nanocarbons. It's an IOP book. And yes, if you are affiliated with a university, your university library subscribes to it. All of them do, because it's in a series of books. So you get it for free. Finally, the hydrated, what about the processes in nature that are about 1 second? MD, once again, 1 picosecond, 10 to the minus 12 seconds, or even more, or a little bit more with less accurate force field. So how to accelerate by a factor of 10 to the 12. So here is what I said verbally. Let me show you on a video screen. Reaction speed doubles when I increase the temperature by 10 Kelvin. So to increase by 10 to the 12, we should raise the temperature artificially by between 200 by essentially 10 times 12 divided by 10 by a logarithm of 2 to the basis 10 in Kelvin. That would be, yes, you will get, this will give you about 400 Kelvin, but the estimate cannot be so precise. So I would say delta T, it's between 200 and 2000, and whatever happens at one temperature, if you raise it by this temperature, delta T, it will happen 10 to the 12 times faster. Well, with this, I thank everybody for their attention.